And he was here for a long time and then escaped. And now he's at California State University, Sacramento. So please introduce you to Scott Gordon, Dr. Scott Gordon.
Well, thanks. It's great to be back. I taught here for 8 years, and every time I drive onto the campus, I wonder why I left. It's very pretty here. But anyway, obviously I'm a professor too, and George told me not to walk around or I could cast a shadow or something. I may not be able to help myself, so I'll do my best. Anyway, the title of my lecture is Recursion Without Fear. This is a talk that I've developed over the course of probably 12 or 13 years. And it's usually interactive, and it usually takes place over about an hour and a half. So this is compressed into 45 minutes, and it's not so interactive. But we'll see if it gets the point across anyway. So it's Recursion Without Fear, and if you read the description of the talk, you'll learn that you also notice that you will learn 3 magic tricks along the way. So watch for the magic tricks. Okay, so it's Halloween. And so recursion seems to be a good topic to come up around Halloween because nothing seems to strike fear in a programmer's mind than the dreaded R word, recursion. So, I mean, how many of you can empathize with that thought? Or you're all just completely, oh, recursion, I love that, I use it all the time, or recursion, and then you faint or something like that. Okay, so how is it that we learn recursion? You may look back and dust off some things and try to remember how it was you learned or tried to learn recursion, learn something about it. Usually we're told what it is, and we see some examples of it. And then, allegedly, we're going to extrapolate from that. So, okay, what have we been told that recursion is? That's typically how it's taught. So here's the big question, what is it? Well, okay, now that's we haven't even seen the magic tricks yet, so it's not magic yet. But okay, what is it? What's the first thing that comes to your mind when you hear recursion? What is it? Okay, well, not the jokes, but what is recursion? It is it's when a function calls itself, right? Okay, you mean something like this? There's a function calling itself, right? Okay. Well, that usually you look at that and say kind of, whoa. All right. Doesn't necessarily immediately give you an idea of why you do it, but anyway, that's a function calling itself. Okay, what else are we told that it is? Well, we're usually told that it's some sort of simple mathematical construct. There's recursive functions. And usually we learn something like this. Does this look familiar to any of you? What's that? Close. What's that? That's the factorial function. Right? Factorial of n is 1 when otherwise f of n minus 1 when n is greater than 1. Not defined for other ones. And the reason this is recursive is because itself. Okay. Any of you less fearful of recursion yet? What is it? Okay, we're usually told. Now, usually at some point, as maybe as you're still frustrated, somebody tells you it's the same as any other function. And that's true. It is exactly the same as any other function. A call is made, an activation record is created at the time of the call, and what's in the activation record? There's 2 things of importance in the activation record. There is the return address, how to get back, and there's all the values of the local variables. And then, when you return, those variables are restored. In fact, for a language to implement recursion, there's usually no need to do anything that isn't already being done. So it's just like another procedure call, or function call. Okay? So basically, this way of teaching recursion is, well, you already know it. Okay, so I don't know. I don't know if that helps either. What else? Well, beyond that, most of the time people will say, well, don't you know it yet? That's it. I actually had a professor once tell me, here's what recursion is. It's when two mirrors face each other. Like that. And you get that tunnel. And I don't know, I feel like if somebody tried to teach me recursion that way, I would say something, is this Java or is this C++? What does that have to do with programming? I think something is missing in that way of learning recursion. I don't necessarily think that kind of approach is going to enlighten you on, or enlighten anybody on recursion unless you're a genius and you make these extrapolations right away. So let's start over again, and I'm going to give you my answer of what is recursion, at least what I think is a more helpful answer, and that is that it is a control structure. And once you decide that it's a control structure, what are other control structures that we know? What are some other control structures? If then. Any others? Switch statement. That's kind of like an if then. While. Okay, so you know some control structures. All right. How do you learn about control structures? Are you told how they're implemented? Language, or are you given a mathematical framework for them? That's not usually how we as humans learn how control structures work. We learn what they do and how to use them. And we practice. So let's start over with a new question. What does recursion do? Let's find out. All right. Here's that first recursive program that I threw up there. This is about the shortest recursive program that I think you could write, even in pseudocode. This is pseudocode here. So, because I left off the semicolons. All right, so this is a recursive program. What will this program do? You run it. Infinite loop. You guys agree with that? What was that? It'll fill your stack up. So is it an infinite loop? If you run this program and implement it, what will it do? There you go. That's what it'll do. So it actually took you guys a fairly long time to answer that question, and this was the shortest recursive program that I could write. But that was good. You got it. That is what it will do. It may take it a few seconds, but it'll fill up your stack and then it'll tell you. It's not an infinite loop. It'll stop because it's doing something. It's making a gazillion activation records. And eventually there's no more room for them. And you get that. Okay. So that's not very useful to use that feature of recursion, right? But we know it's doing something. All right. Let's make it a little bit, let's add a little bit to that piece of code. Here was our original piece of code, all right? Let's add something to it. Let's print something out in there. Okay? Same code, but I've added the print statement there. Now what's it going to do? It's going to print high until I get the stack overflow, right? So it's going to do something like this. And then I would need a lot more slides to display everything. But if we fast forward about 1 million slides or so, eventually you'll get this. Now this is actually a little bit more revealing than the last example, because the last example all we saw was the Stack Overflow. This time, at least we know that it's getting called lots and lots of times. And then we get a Stack Overflow. All right, let's make the program a little bit more interesting. Let's make it stop. Now, to make recursion stop takes a lot of start. It was easy to make it start. To make it stop, you actually have to make something change. And the simplest way to make something change is to add a parameter that you change. And then check the parameter. So this is about the shortest recursive program that I could come up with that stops. So notice the difference. The last one didn't have this if in there, and it didn't have the parameter, and there wasn't the initialization of the parameter on the call. Okay? What's this program going to do? It's going to print hi 3 or 4 times, something like that. Right? In fact, if you run this program, it's going to do that. Let's take a look at that code again. It's very important because now actually we're bringing recursion under control a little bit here. Okay, so this has a parameter. Why? Because something has to change, otherwise it will Stack Overflow. If nothing changes, it'll Stack Overflow. So something here has to change. The way to do that is to put a parameter, change the parameter. That's how you get recursion to eventually stop. Also, the way we set it up may affect how many times we can get this thing to print hi. Okay? Now, I'm going to add something to this code. And that is, instead of printing hi, I'm going to print n. That's the change of the code is I printed n instead of printing hi. So now what is the code going to do? Okay, some of you already have the answer right here. Instead of printing hi, 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 it's going to print 1, 2, 3, 4. See that? Let's go back to the code. First time first time into the code, n is 1, and that's what it's going to print. And it's going to call itself with n plus 1, so then it'll print 2, and so on. And we'll get 1, 2, 3, 4. Now, I'm going to make a key change. Indicate this print n here. It's going to be exactly the same, except I'm going to also have print n after the call. Okay? Now what's it going to do? Okay, here's what it's going to do. 1, 2, 3, 4, 4, 3, 2, 1. Let's take a look at that code there. Again, I have 2 print ends. We know what the first print end did. That made the 1, 2, 3, 4. That second print end must be making the 4, 3, 2, 1. In fact, if you were to remove this print end here, and you instead only had the print end here, which portion of this would print? Only the second half, the 4, 3, 2, 1. Because that first print end is what caused the 1, 2, 3, 4. All right, so here's that code. I'm going to make one extra little change. Just to verify that, I'm also going to print the letter A for the first print and the letter B for the second print, just so we can make sure which print is responsible for printing which number. Okay? And we get this. All right, so that first print gave us the 1, 2, 3, 4. The second print gave us the 4, 3, 2, 1. Now, if you look at that code, the only difference between this print and this print are positioned relative to the recursive call. This print appears above the recursive call. This print appears after the recursive. So we built ourselves a loop. Call that loop A. That runs in the forward direction. And we got a loop B running in the backward direction. Now, for the whole rest of this lecture, this program right here is going to be sort of the canonical program that illustrates the fundamental function, what recursion does. And what I've doing is I've got a version of this program in C and Java that you can take. Hopefully, there may not be enough to go around. I've got 30 copies of it. It's the same code, except a C++ version and a Java version of exactly the same code. You'll see it's really not much bigger. There's some semicolons, and one says C out, one says system out. That's about the only difference. Okay, so forward loop, backward loop. Oops, there's our canonical recursive program that illustrates the behavior you get if you stick a recursive call in your program. And now we're down to the first magic trick, and that is when you put a recursive call in your code, you get 2 loops for the price of 1. One gives you 2 separate loops. If you want to make a loop that goes in the forward direction, simply place that code above the recursive call. If you want to make a loop that goes in the backward direction, simply place that code that you want to loop in the backward direction below the. You don't have to use both of these loops. You can use or was it just short? If there's extras, looks like there's everything good. Okay. So I may refer to that occasionally. So if you've got it in front of you, that's great. Okay, that's your first magic trick. Now the next thing is a bedtime story. I know that it's about lunchtime. If I did this at 2 o'clock, it would be disastrous, but we should be safe if we do it now. This book was written in 1954 by Elizabeth Burroughs, and it's a cute little book. I think it was last in print about 15 years ago in a little tiny golden book that was about this big. But this is a over 50 years old book. I believe this book actually predates actual computers that implemented recursion. Were there any, George, were there any languages that implemented recursion before 1954? Except Prankelcool? 1954. Right. Okay. Here's the story. Once upon a time, there was a little girl. It was time to go to sleep. Oh, by the way, I have to admit, I didn't get permission from the publisher to display this. But I did get permission from the family of the author. Because I tried. I couldn't. The publisher won't write back to me. But I did talk to the family of the author. And they did give me permission. I don't know if that's legal or not. But okay, so once upon a time, there was a little girl. It was time to go to sleep, but she was not sleepy. Maybe she was just a tiny bit sleepy. She hopped into bed and covered herself up to her chin with her big red blanket. She said to her mother, "Tell me a story." So her mother said, once upon a time there was a giraffe, a little giraffe with a long. It was time to go to sleep. He was not sleepy. Well, maybe he was a tiny bit sleepy. He said to his mother, "Tell me a story." I like the picture. They have a house plant, and it's a palm tree. So his mother said, "Once upon a time there was a fox, a little red fox with a big bushy tail. It was time to go to sleep." He was beginning to be very sleepy. He said to his mother, "Tell me a story." So once upon a time there was an elephant, a little gray elephant with a big trunk. It was time to go to sleep, and she was beginning to be just a little bit sleepy. So she said to her mother, "Tell me a story." was a very sleepy little mouse. She said to her mother, "Tell me a story." I love this one. They made a sled out of the mouse trap, and the little mouse is sleeping in a matchbook. I just love the pictures in this book. So her mother said, once upon a time there was a pony, a little brown pony with a thick black mane. He was a sleepy, sleepy little pony. He yawned. Then he said to his mother, "Tell me a story." This is my favorite picture in the book. He took off his horseshoes before he went to sleep. So his mother said, "Once upon a time," but the little brown pony did not hear. He was fast asleep. So was the little gray field mouse with the long skinny tail. So was the fluffy black puppy with the floppy ears. So was the little gray elephant with the big, big trunk. So was the little red fox with the big bushy tail. So was the little giraffe with the long, long neck. And so was the little girl all cuddled up in her big red blanket, all fast asleep. Good night. Isn't that a great book? I love that book. So now the obvious question, since you're all computer scientists, would be, I bet I could write that story once using recursion. Hopefully you detected the analogy with the previous examples, right? All the elements are there, actually, in that story. We should be able to do it. Why? Because there are two loops. One of them is going in the forward direction. That's this one. That's the part that was all those once upon a times. And it went the girl, then the giraffe, then the fox, then I don't remember all the order of the animals. Then there was another loop that was so was the pony, so was the fox, so was the giraffe, and it ended up back at the beginning with so was the girl. That loop ran in the backward direction. Now, I didn't mention this, but in your handout, on both of the examples and also in the pseudocode, was an if statement, where we were checking to see if it was time to stop that first loop, right? And what do we call that? That's the base case. Did this story have a base case? What was the base? What's that? Well, actually, that wasn't the base case. The little girl was a tiny bit sleepy. But do you remember which animal the base case actually hit on? It was the pony. And what was it about the pony that made it the base case? She was asleep. There was no need to tell the story because the pony was asleep. So the base case, there is a base case, and was the pony was asleep. All right? All right, so I think we can take this model right here and write this story much more efficiently. Maybe a little less artistically, but much more efficiently. Something like this. Now you should be able to take your code, hold it up to that one, and make a virtual one-to-one correspondence between that canonical recursive code that we built and that you have sitting in front of you, and this code. There's the program statement in the initial call. There's the definition of the function with a parameter. There's the portion of the code that we want to loop in the forward direction. Then there is the recursive call that changes the parameter. There's a test on that parameter. And then comes the code that we want to run in the backward direction. The exact same structure as is on your handout. There's the code in red that goes in the forward direction. So that means we're going to say once there was a something, such and such was whoever it is was sleepy. So our mother said that all goes one after another in the forward direction through the animals. This one happened after that first loop was done. Then started this loop. So was the pony, or not, no, it didn't say so was the pony. We actually had to doctor up the if statement a little bit so that it didn't say so was the pony. But I think it was so was the fox, so was the dog, so was the field mouse, and so on, backwards out to so was the girl. That one ran in the backward direction. And look at, the key is where this code is positioned in the function relative to the recursive call. The recursive call is here. Any code that runs before it will loop in the forward direction. Any code that appears after it will loop in the backward direction. If we run this program, I guess we have one little detail, and that is these x's. Where are we going to get this data? Well, let's see. We want to start with the first animal, which is the girl. And then for the next story, we want to go to the next animal. There's different ways we could set that up. Let's do it the simplest way. Let's try an array. So for the book, we could have an array, say with, it turns out there's 7 animals in this story. That maybe we could use 3 parallel arrays, 0 to 6. The first one has the actual type of the animal. The second one has, each animal had a different attribute. So like the girl had a red blanket, the giraffe had a long neck, the pony had a thick mane, and then the last one was how sleepy they were. And of course, our base case is going to be testing for asleep, because that's what's going to stop the loop. So when we hit the asleep. If we do this, and we set it up that way, I could write that story in C++. Here's the sleepy story in C++. And again, you should be able to take your code, hold it up to that, and match it pretty much perfectly. I did take the liberty of reducing the number of animals from 7 to 4 so that it would fit on the slide. But if you want to make this all 7 animals, you could just add those animals to the arrays. So at the beginning, I've declared an array called kid, which are all the different animals, and how sleepy they are in this array called sleep. I didn't take the liberty of putting the attribute red blanket and that in, but that could be easily added. And I've only did it for 4 of the 7 animals. But here's the recursive program, and here's the main down here, because C++ likes to have the main. Well, I could put the main up, but then I'd have to forward reference the story. So it's simpler to put the main at the bottom. And my parameter is going to be an index into the array. So the first time through, I'm going to tell the story on the 0th animal. And A will be 0, and that'll refer to kid 0 and sleepiness 0, which will be girl and awake. Here is the recursive call right here, story A plus 1. So here's the recursive call right here. Here's the portion of the code that I want to go in the forward direction. Once there was a girl, she was awake. Her mother said, okay, then we continue. Obviously, it's a slightly simplified version of the story. I wanted it to fit on the slide. Here's the base case and the call. Where's the call? Here's the base case and the call. Here is, after the recursive call, the portion of the program that will loop in the backward direction. So was the, and notice that the item here that I'm going to print is identical to the item here. So that the first time through it'll say girl, and then on the way out it'll also say girl. 2 loops, 1 control structure. In this case, I'm using both of the loops. If all I wanted to do was had a story that said so was the, so was the, so was the, so was the, for those animals going backwards, I could just remove this code. If I didn't want the so was the, and all I wanted was the once upon a times, I could remove this code. Any questions about this little piece of code here? Can you see by taking your canonical example what corresponds to what on there? Okay, let's carry on. When you run it, it looks like this. Forward loop down to here. The base case test caused this, and then I get the backward loop through the animals. Okay, so I wrote the story once, recursively, and there it is when it runs. The forward loop, then the backward loop. To make this, the base case here was a little convoluted. It ended up being an if-then-else because there was a special case. In the case of the pony, we say something different. So that particular base case I had took a little bit more code than your canonical example. If you have to handle the base case separately, then you just put it in that if. You deal with it there. Okay. What if we didn't use an array? What if we used a linked list? What if we had a linked list of objects, say, instead of an array? Just say a simple forward linked list. So an object has an animal, a sleepiness, and a next. Simple forward linked list. What would change about the program? Well, instead of indexing how sleepy an animal is with this array subscript, I would instead be using a field indicator with a dot. And then, instead of going to a plus 1, I would need to go to a dot next. And my definitions would change at the very beginning. I wouldn't have arrays. I would have to set up a linked list. Other than setting up the linked list, these are the only things that would change. Is how I print something out, because obviously it won't be an array. It'll be a field. That's here. And how I go on to the next one. Okay, so but I have to do that backward. The so was, the so was, the so was, the so was, the. I have to go backwards. That second part of the story goes so was, the so was, the so was, though, and it's going backwards. Has to go backwards through the animals, right? So my linked list only goes forwards. Do I need to add some backward links so that that second loop can go backwards? The answer is no. So when you've traversed a linked list, when you've had to, I'm sure you've had to work with linked lists. If you're in a situation where you have to traverse the linked list both ways, or if you've got a linked list and you need to traverse it backwards, invariably what happens is you think, oh, I've got to go add backward links. My data structure is going to be more complicated. It turns out, in this case, we don't. That's the second magic trick. You can traverse a linked list backwards without backlinks using recursion. Because in that program with the sleepy story, we could have printed just the so was the, or in your code here, if you changed it to where instead of just incrementing a number and printing that out, you had it walking through a linked list, it will go down that list in the forward direction, and then as it's popping the stack, you'll go backward through it in the backward direction. And if all you wanted to do was traverse it in the backward direction, what would you have to do? Close. If all you wanted to do was go in the backward direction, you would place the code where? You would put your code after the recursive call. So if you need to traverse a linked list backwards and you don't have backlinks, you can do it with recursion. You start your function with the recursive call that takes you to the next element, and then the code that you want to process on each element you place after the recursive call, because that's where you get the backwards loop, is in the code that appears after the recursive call. That traversal, the backward, is being handled for you by the runtime stack. Okay, now I promised you 3 magic tricks, and there's one more magic trick to show you. I claim that none of the programs that I've shown you have any variables in them. Now, you probably are thinking, Scott, now you've finally gone berserk, because I can see some variables there, and I can see a variable there. Right? That looks like an integer variable called a. And that looks like a very complicated variable, that array variable called kid, and that other array variable called slp. Okay, those aren't variables. Those are constants. If I stick the word const in front of every one of those things, the program still works the same. What's a variable? A variable is something that changes. What does it mean for a variable to change? That means that you say put it on the left-hand side of an assignment statement. Now you might say, whoa, wait a minute. You are incrementing the variable right here. You're saying, aha, I've got you now, Scott. That is not an assignment statement. That's an expression. That is evaluated. A is not changed. If A is 4, A will still be 4 after that statement is done. In fact, it's very important that it still be 4 so that on the backward loop, we print out the 4th kid. This does not change A. In fact, this will generate the value 5, and then 5 will be used to initialize the constant in the next iteration. Yes? No. A++ would be a bad idea. In fact, A++ is would indeed violate. In fact, it would kind of mess up our. If we used A++, it would mess up the whole structure. Because not only it would work fine until it would work fine in the forward direction, but then it would screw up the backward direction if we did A++. Because then when we went on the backward direction, then what would happen is when we printed so was the, this would be a different kid on the way out. It's important that this A or that this stays the same so that we get the backward loop on the same items. Okay? So here's our third magic trick. You don't even need any variables. All right, so did you ever imagine that you could traverse a forwardly linked list backwards without even using any variables? I think that's a magic trick. But recursion lets you do it. Basically, when you do a recursive call, it generates these loops, and one of them is being handled by the runtime stack, and your code is sort of along for the ride. You've got some code that's along for the ride above the call that's going to run in the forward direction. Any code that appears after the call is along for the ride in the backward direction. You can piggyback off one or both of those. The author of that book, by the way, Elizabeth Burrows, died in 1975. She lived most of her life in Stockton, California. And her son became a pioneering computer scientist. She herself was not a scientist, but I did speak with her grandson, who said that she was a very, very intriguing woman who had a lot of interest in science and math, and was interested in all things technical and new. And I think that shows pretty well in her book. Her book foreshadowed recursion so clearly. All right, that's it. I guess my other magic trick was I finished 4 minutes early. I was imagining, yes.
Did you give her grandson a copy of your program?
That's true. I could say, look, I've improved her story. I've made it much more efficient. You can now publish it in one page. The kiddies will love this version. In fact, yes.
You use ++A when you have the same
error. Yeah, you'd have the same problem because it will still increment. Well, no, actually, if that's an interesting question. We could answer that question by looking at this code here. If we said ++A, the interesting thing is that it would not damage this because it will have already printed it out for A. But it will, in fact, increment A, and whether we have the ++ before or after, it's still going to increment the A before it executes this code. And so the backward loop will still be incorrect for the same reason as if it were A++. However, let's see, when you do ++A on a call in C++, I don't remember whether it increment, well, it would have to increment then before it makes the call. So it would make the same error. Yeah. Good question. You can keep these, by the way. I don't need them back. Oh, those are extras. Okay. By the way, there are languages that don't allow you to use variables. For instance, scheme, or I did, and in case you think that is unusually restrictive, all of my graduate work and all of my experiments, which involved mostly genetic algorithms, but also some neural networks, I wrote all of my code in a language called Sisal, which was a pure functional language, single assignment, no variables, no loops. And so that is not an undue restriction. Recursion gives you all the looping behavior that you need. And so if you understand the power, but it takes some practice. I'm not going to pretend that now I have anointed you with this magical skills, because it still takes practice to leverage that. Yes.
At some point, you get performance benefit using recursion, or
So the question is, do you have performance benefit using recursion? Generally not. Usually you take a performance hit, because the same loop you can usually write more efficiently yourself.
So you do it just to kind of simplify your algorithm.
You can use it to simplify your algorithm. You could use it because the language requires it. Sometimes it can dramatically simplify your algorithm. And these days, more and more of our programs don't have performance requirements. Back 30 years ago, almost all programs had performance requirements, and you had to write them efficiently. Otherwise, you'd be in trouble. These days, the number of programs for which performance is a serious issue is gradually going down. So you can get away these days with writing more elegant code. No, you wouldn't necessarily want to always use recursion if you didn't have to. But you shouldn't shy away from it just because it's scary, is what I'm saying. Okay, well, thanks for the great questions. You were a great audience.